Okay, this is the remaining problems from section 2.5, similar to the ones that we went over in class. This gives you some more variety and hopefully will help you master these concepts. So let's look at example 1. We did B part in class, so I want to look at A. This is an absolute value equal to a positive number. As long as the right side is positive and the absolute value is isolated, you're able to solve it. If it's isolated but this is negative, remember that would be a no solution. So to solve this, we need to set the inside equal to the two possibilities that would make a distance from 0 be 2. So if this was a negative 2 inside, that would have an absolute value of 2, or if it was a positive 2 inside. So we think of setting the inside equal to negative 2 or the inside equal to positive 2. The inside is just x minus 5. So x minus 5 equals negative 2. X minus 5 equals positive 2. If we add 5 over to this one, we get 3. And if we add 5 on this side, we get 7. So 7 and 3 are equidistant from 5. And in fact, they are 2 away from it. The other example from the absolute values is C. So in this one, this is not isolated yet, so we want to subtract the 5 over. This is absolute value of x minus 2 equals 0. That is able to be solved, but it's because it's not negative. It's not really positive either, so this is only one scenario. You can't make a negative 0, so you'd only have one way that this can be 0. So anytime your absolute value equals 0, you only get a single solution, but all other times you get two possibilities. And that's all there is to absolute value equations. So let's look at the next subset. I skipped over both of these because they were a review of factoring. So for this first one here, we want to try to factor by grouping because this is 4 terms. So I'm going to pull an x squared out of the first pair. That leaves me with 3x minus 4. I'm going to pull a negative 9 as a common GCF out of the second pair, and that also leaves me with 3x and minus 4 because the negative pulled out changes that 36 to a negative when you divide. Notice that we get a matching 3x minus 4, but we also get an x squared minus 9, and x squared minus 9 factors again. It's two perfect squares, and it has a minus sign between them. So we get an x plus 3 and an x minus 3 equal to 0. So anytime you have this completely factored, you set each part equal to 0 and solve for the pieces. And x minus 3 equals 0. These last two are pretty easy. This would be positive 3. Subtract the 3 on this one. This would be negative 3. And we'd have to add 4 and then divide by 3. So the last one is 4/3. So 3 different solutions. Now the next part, B, is a little bit different. You could try pulling something out on each side, but that's actually not the best approach. When you want to solve by factoring, you should get everything on one side. So I'm going to move the 2 terms on the right over to the left and just tack them on here at the end. So this would be minus 6x cubed and plus 8x squared equals 0. We don't have a number GCF because 15 is not divisible by 2 and not all of them are divisible by anything else. So we need to pull out an x squared though because they do all have an x squared in common. So that would leave me with 15x to the third minus 20x squared minus 6x plus 8. If we factor by grouping, notice I'm going to keep bringing my x squared down. This would be 5x squared, and that would leave me with 3x minus 4. Pull out a negative 2 in the second pair, and that would also leave me with 3x minus 4. We have my x squared out front. So this ends up being a 3x minus 4 that they have in common and a 5x squared minus 2. Now notice there is an x squared in this binomial, but these are not both perfect squares, so that's as far as that can go. So we set each of these equal to 0. X squared equal to 0, you take the square root of both sides. That'd be a plus or minus, but 0 is just going to be 0. Plus or minus doesn't change it. 3x minus 4 equals 0. We would add the 4 and divide by 3. So another solution is 4/3. And the last one is 5x squared minus 2 equals 0. We would add 2 over, trying to get this to be x squared by itself, so we can do the square root again. Divide by 5. And I'm going to take a square root of both sides, remembering to put in my plus or minus on the right side. So using that something squared equals a number, that square root method. And unfortunately for us, this needs to be rationalized. So I have to multiply top and bottom by square root of 5 to get this to be a perfect square in the denominator. So my last solution is x equals plus or minus square root of 10, because it's 2 times 5, over square root of 25, which is just 5. Now you cannot reduce that 5 and that 10 because one of them is under a radical and one of them is not. So there are 1, 2, 3, 4 solutions here for this problem. And that's because 0 occurs twice. There's actually 5 solutions, but 0 happens twice because of the x squared. Okay, we covered this in class, but I think I'm going to redo the topic again just to make sure we've got it. When you're asking someone to find the real solutions of an equation and you're given something with a rational exponent, there's a property that says if u to the m over n equals, let's say, d, you can solve that by using the reciprocal, remember, to get rid of this power on the left. Okay. Now the problem with this is because this is flipping this fraction, we don't know, first of all, if the solution is going to exist, because there is differences between if the numerator and denominator are both odd or if one's even or one odd. So we have to be careful there. The first thing you should always check before even starting this type of equation is the bottom root right here is a 5. If it's odd, it is okay for there to be a negative on the other side, at least for now. So then we're going to raise this to the 5/3 side, power on each side. So that would be x, and this would be the third root of negative 27 if we convert it to a radical, all raised to the 5th power. So cubed root of negative 27 is negative 3. Raised to the 5th power is negative 243. So there's that one. This scenario, this is a negative over here again, so that means we definitely want to start out with an odd root in the bottom. But notice there's an even root on top. You'd think, well, that doesn't seem like it would be a big deal, but as soon as you go to flip this, this becomes 3/4. And by the way, anytime you do anytime you take a root by doing these powers on both sides, if an even power ends up in the bottom, you really should write plus or minus on the outside of the other side. Just like taking a square root of both sides requires us to write a plus or minus. That is not true when you're doing an odd root when you flip it. So if the denominator is still odd, then you don't have to do plus or minus. But if the denominator is even, you should be putting a plus or minus. So this is to the 3/4 power. And then we would convert that to x equals the fourth root, plus or minus, sorry, the 4th root of negative 49 all cubed. Now, unfortunately, that's as far as we can go because this is not a real number. You can't have an even root with a negative underneath it and say that it's a real number. It's not. So for this one, the answer is there's no real solution. So no real solution. Here, I don't even have to solve this problem at all because you can't have a 4th root equal to a negative number. Okay? An even root cannot equal a negative. So we don't even have to solve that. Although if you did, you would get a solution, but it does not plug back in correctly. So that's, remember, these are radicals, so if you check your solution, you'll see that it will not plug back in correctly. Because what you would get would be cubed root of negative 8, which is negative 2, and then you raise that to the 4th power, which is positive 16. positive 16 to the 3/4 is 8, not negative 8. So it does give you a problem. Okay, so I have a couple more of these just to look at real quick. Let me scoot this down a little bit. So for this one right here, it's an odd root on the bottom, and this is positive, so there's no issues with that. When I go to flip the fraction here to cancel this, I end up getting an even root on the bottom, so that means I need a plus or minus on the right side. And this would be x equals plus or minus the square root of 25, and then it gets cubed. This time I can take the square root because it's a positive number inside. So this would be plus or minus 5 cubed, and that means that it's 125 but with a plus or minus out front. So two solutions here, positive 125 and negative 125. And they both will work when you plug them back in, because you'll take the cubed root, so you'll either get a positive 5 or a negative 5 depending on which one you plug in, but then you square it, and positive squared is positive and a negative squared is a positive. So that would work in both scenarios there. This one's okay. It starts out with an even root, and the number on the right side is positive, so that means there's no issues with that. When we flip it, we end up getting an odd root on the bottom, so we don't need a plus or minus. The only ones that need the plus or minus added on this side is the ones that end up with a, when you flip it, you get an even in the denominator. So this would just be x equals the cubed root of 27 squared. And the cubed root of 27 is 3, and you square it and you get 9. So one single solution. Okay, we went over one of these in class. I'm going to do the rest right now with this video. And this is solving radical equations. We use something called the power rule, which says if you want to get rid of a radical, you can raise both sides to the same power, like squaring both sides. The only problem is when you do that, anything that had a negative base originally ends up being positive. So you may get that your two sides of your equation are not balanced still, and that means we have extra solutions or extraneous solutions. So the steps to solving a radical are to get the radical on one side by itself, raise each side to the power equal to that root so that it'll go away. If you still have a radical, and I'll do one example where you have two radicals and you have to do the process twice. You repeat steps 1 and 2. If you don't have two radicals, or if you don't have a radical still left over, you go ahead and solve. Check all of your solutions, because remember, by squaring or cubing both sides, we could have created an extra solution. And then there's just one other thing to note. We'll talk about this a lot more in Unit 2. Domain of a radical equation. If you're doing something like the cubed root of x, with cubed roots, the inside can be negative or positive, so the domain is any real number. If you're doing the square root of x, you don't want a negative underneath here. So what we say is that x has to be greater than or equal to 0, because we can take the square root of 0. So that's just something to note, that if you have an odd root, it's any real number you want to plug in. And if it's an even root, it has to be a positive number underneath here to be able to do this in the real numbers. So we're going to start off with A, because I did a little bit farther down was the example that I picked to do it in class. This is isolated already on this side by itself, so we're ready to get rid of it by squaring both sides. If you square this, square root and a square cancel, and that would just be 2x minus 9. 1/3 times 1/3 would be 1 over 9. You can either add the 9 over and then divide by 2 the way this is, but you'd have to get a common denominator. So I'm actually going to choose to multiply everything by 9 to get rid of that fraction, and I can do that because there's an equation. So this would be 18x minus 81 equals 1. We would add the 81 over, so that's 18x equals 82, and we divide by 18. And it looks like both of those are divisible by 2, so that would be 41 over 9. Now, I have to check this solution before I circle or box it. So I'm going to go back over here and show 2 times 41 over 9 minus 9 under the radical equals 1/3. So 2 times 41 is 82, so 82 over 9. Think about this being 9 over 1. So you can get a common denominator here to subtract. Multiply this by 9 over 9. So I get 82 minus 81 over 9. And 2 minus 81 is 1. So the square root of 1/9 is 1 over 3. And it is okay because this is positive inside and this is positive. Anytime you're dealing with a square root and they do not have a plus or minus out front, you are supposed to go with a positive root answer. So this one is a check. Okay, let's look at B. Let me mark this off. B is a cubed root, but it's not isolated, so we need to move that 5 over first. So subtract it to the other side. We're going to cube everything to get rid of the cubed root. This would be 6 minus s squared equals negative 125. We need to subtract the 6 over. So negative s squared, don't forget that negative there, equals negative 131. I would divide both sides by negative 1 so that we don't have to deal with that negative in front of our s squared. And then this is taking a square root. So s equals plus or minus the square root of 131. Now, you should check both of these solutions, but when you're dealing with odd roots, there shouldn't really be any issues. But I'm going to show you the check real quick. So I'm going to do it down here. So this would be the cubed root of 6 minus the, let's do the negative one first. So negative 131 under a square root squared plus 5 equals 0. This right here gets squared, so it actually turns out, and that cancels it. So be careful. The negative 1 out front is going to get squared, which makes it a positive 1. The square root gets canceled out when you square. So this actually ends up being 6 minus 131 plus 5 equals 0. That would be the cubed root of negative 125 plus 5 equals 0. Cubed root of negative 125 is negative 5, because remember you can have a negative with an odd root, and negative 5 plus 5 is 0. The same thing is going to happen when you have the positive square root underneath there, because when you square this, you're just going to get rid of the radical. So you end up with the same problem exactly because of this guy getting squared. So this one checks out as well, since we already know that this one was identical. So both of those solutions are valid. All right, let's look at C. This is already isolated, so we just need to raise both sides to the 4th power. That would make this 2x squared minus 1 equals x to the 4th. I would like, since this looks sort of like a quadratic, I'm going to move everything to one side. In fact, I'm going to move everything to the right so that my x to the 4th stays positive. So this would be a minus 2x squared and a plus 1. You can try to factor this, especially since, and this is just a trick I learned a long time ago. Whatever the highest power is, if you think your trinomial is factorable, the middle power has to be half of that. That's kind of a little pattern to kind of see if you should even attempt factoring it. So the only thing is this breaks down into an x squared and an x squared instead of an x and an x. Factors of 1 are just 1 times 1, and if they were both negative, then we would be able to factor that. It multiplies to positive 1, it adds to negative 2. This is 2 perfect squares on both of them, so this factors into x plus 1, x minus 1, because that's the square root of both of those, and we get another x plus 1, x minus 1. So I only have 2 possible solutions here. Either x is negative 1 or x is positive 1, because some of them appear twice, but it's just solve it once instead of solving it multiple times. Now, we need to do a check for this. So 4th root of, I'm going to do the negative 1 first. 2 times negative 1 squared minus 1 equals negative 1. I already know that this is wrong because even roots cannot equal a negative answer on the other side unless there's a negative in front of the root, and there's not. So this does not work, but I'll show you the whole thing. Negative 1 squared is 1 times 2 is 2. 2 minus 1 is 1. The 4th root of 1 does not equal negative 1. So that means this one's out. If we have a positive 1 underneath there, we'll be fine because this ends up being 4th root of 1 equals 1. So positive 1 is the only solution that works. Okay, we did E in class, so I'm going to do D right now. This is not isolated yet. To be able to solve these, you need the radical isolated. So I'm going to add the x over to the other side. It doesn't matter if you put it in front of the 3 or not. I like things to be in descending order. I'm going to square both sides. This is new because this is one like we did in class. This has to be FOILed now because there's a binomial on that side. So this is 3 minus x because square root and square cancel. And then we get x squared plus 3x plus 3x plus 9. So what I did there was I worked out x plus 3 times x plus 3. So that's that. Combine like terms on the right side. And then move everything over to be together. So minus 3 and plus x. So I'm getting 0 equals x squared plus 7x plus 6. You should see if it factors. It does. It would be a positive 6 and a positive 1. That multiplies to 6 and adds to 7. So my possible solutions are negative 6 and negative 1. So let's check those. It's easier for me to check it after I've isolated the radical. So I'm going to do my check by plugging everything into the square root of 3 minus x equals x plus 3. So if we plug in negative 6, 3 minus negative 6 equals negative 6 plus 3. 3 minus a negative would be plus, so this would be 9, but this is negative 3. This is positive 3, so this does not match. So that means negative 6 is out. If you plug in negative 1, 3 minus negative 1 equals negative 1 plus 3. This is square root of 4, but this is positive 2, which is what that equals, so that one is okay. So it is really important that you check those solutions because a lot of times you have an extra solution that does not work. All right, so we're going to look at F next, and then G is the fun one, so we'll talk about it. And then that will be the end of what we're going to do on the video because I'm saving the last new topic, one we haven't seen, for the Tuesday class session and the Monday class session if you're in my Monday, Wednesday class. So again, this one is not isolated, and I don't like that negative in front of this radical. That's something I try to avoid. So if I was going to fix this, I'm going to move this guy over by adding, and I'm going to move this guy over here by adding, because they're both negative. So that would be x plus 2 equals square root of negative 7x minus 24. Now it's okay for this inside to look like a bunch of negatives because we don't know what x is. If x is negative 8, then that would turn into a positive 56. So because we don't know what x is yet, it's okay that there are negatives underneath here. So we need to square both sides. So we're going to square and square. This needs to be FOILed, so we're going to do x plus 2 times x plus 2. This will just cancel the radicals, so that'd be negative 7x minus 24. FOIL this out, 2x plus 2x plus 4. Combine like terms on the left. And then we're going to move everything over to be with the x squared term. So I'll add 7, which makes this 11. And I'll add 24, which makes this 28. And then that factors into x plus 7 and x plus 4. So I get negative 7 as a possibility and negative 4. So we have to do our checks. Remember, this is crucial for radicals. I'm going to plug it into this scenario right here. So x plus 2 equals the square root of negative 7x minus 24. It's always easier if the radical is isolated when you plug back in. So I'm going to do negative 7 first. Plug it in for all the x's. That's negative 5 equals the square root of 49 minus 24. And that would be 25. But remember, a square root out here without a negative in front of it has to equal a positive of that number. So that means that negative 7 is out. And guess what? In this one, negative 4 is also out. I know that right away because it makes this side over here negative. With even roots, that just can't happen. So this is negative 2. This is 28 minus 24. and that gives me square root of 4, but square root of 4 is positive 2, not negative 2. So no solution. It is possible to go through all this work and get neither one of your solutions work. All right, so my last one to do on the video tonight is this one with two radicals, because I said that this is one of the steps up from up above. It said if you isolate a radical and get rid of it, you could still have a radical in your equation. That happens when you have two radicals and a third piece, like a -1 over there. So the first thing is you have to get one of these radicals to go away. I typically don't like a negative in front of a radical, so I always move that one over and then just focus on getting rid of this one. So this would be square root of 2x plus 11 equals -1 plus the square root of 5x plus 1. Just move the whole thing over by adding it. Then we try to get rid of this square root right here. The only thing wrong with this is it creates a binomial that we have to square on the right side that has a radical in it. So over here we get 2x plus 11, just like we have every time we've squared a square root. On this side we need to write this twice and FOIL it because we have a binomial squared. So we have 2x plus 11. -1 times -1 is +1. -1 times this square root would be negative square root. Square root times -1 would be another negative square root of 5x plus 1. And this is cool. Positive times positive will be positive, and we get the same guy twice. So he's square root of 5x squared, square root of 5x plus 1 squared. The square and the square root will cancel on that. So I'm going to try to clean this up a little bit. I have a 1. That is not to be combined with this, by the way. These are not like terms. This 1 and this square root have nothing in common. They're not like terms. But these two are like terms. They both have that square root. So this is -1 and -1, so that would be -2 on the square root of 5x plus 1. What I meant by these have nothing in common is you can't say 1 minus 2 here. That does not work because this -2 is attached to that radical. And this would just be 5x plus 1 now because this is canceling out. Usually what I recommend for students is to move everything that's not attached to this radical over to the other side. So you might want to clean up this first by adding the ones together. This one and this one are both regular numbers. So I have -2 square root of 5x plus 1 plus 5x plus 2. So I'm going to subtract 2 over and subtract 5x. That makes this -3x plus 9 equals -2 square root of 5x plus 1. And this is where you go, oh no, I still have a radical. So this is where we have to, what I call lather, rinse, repeat. Some people will divide the -2 over because they really want that radical isolated. Unless this number divides into those two evenly, I don't suggest that because you'd be creating fractions. So to get rid of this radical, I am going to square both sides, but because this is times, not adding between these two pieces, you can square them both. So this would be -3x plus 9 times -3x plus 9. This would be -2 squared, which is 4, and then in a parentheses, you'd have what cancels here, which is the 5x plus 1 is the only part left over. So we need to FOIL and distribute everything out. -3x times -3x is positive 9x squared. -3x times 9 is -27x. 9 times -3x is another -27x. 9 times 9 is positive 81. 4 times 5x is 20x. 4 times 1 is 4. Try moving everything to one side, get your common denominator or your common like terms together. I'll do that first. So that's -54x. Bring everything else down. Subtract my 4 over. Subtract my 20x over. And I get 9x squared minus 74x plus 77 equals 0. Oops. I'm going to try to create some more space for this one. So we would need to try to do because 9 doesn't divide into all of those, and neither does 3, I don't believe, but we'll double check. Because if 3 divides into all of them, that would be wonderful. Nope, it does not divide into them evenly. So we need to do 9 times 77, and we're going to have to find our factors of that, which is 693. 1 and 693. 2 does not go into it. It is divisible by 3. 3 and 231. 693 should not be divisible by 4, but I'll show you. 693 not divisible by 5. Is it divisible by 6? Nope. 693 divisible by 7. 7 and 99. 693 divided by 8 does not go evenly. 693 divided by 9 is 77. 693 divided by 10 will not work, but 11, let's see, 11 and 63. And that's going to be my magic pair, because this has to be same sign since it's a positive when we multiplied, but they have to add to negative 74, so they're both negative. So I would have 9x squared minus 63x minus 11x plus 77 equals 0. Pull out a 9x in the first pair, and you get an x minus 7 left over. Remember to pull out the sign of the leading group next. Negative 11 also leaves me with an x minus 7. So I get an x minus 7 and a 9x minus 11. If I solve those, I get a possibility of positive 7, and then I need to solve this one by adding 11 and dividing by 9. So 11 ninths is another possibility. And you think, wow, that was a really long problem. Yeah, it is, and it's a radical, so you still have to check your solutions. So to save some time, I'm going to work this. I'm going to show you what it looks like written out, but then I'm going to work it out in my calculator, just so we can get through that one, because that'll be a lot of showing my work. So I would have square root of 2. The first answer will be a 7. I'm going to go with that because that was an easy check. Minus the 5 times 7 plus 1 equals negative 1. Now, just because this is a negative over here does not mean that this is not going to work, because you have two radicals with subtraction between them. So that would be 14 plus 11, so that would be square root of 25. So that's 35 plus a 1 underneath there, that's 36, so minus the square root of 36. That's 5 minus 6, which does equal negative 1. So the 7 is definitely a solution. I didn't need the calculator for that one. So I'm going to go circle the 7. This is the one I'll probably use my calculator for. So 2 times 11 over 9 plus 11 minus the square root of 5 times 11 over 9 plus 1 equals negative 1. Okay, so let's use our calculator. So 2 times 11 divided by 9, I'm not worried about if it comes out to a decimal right now, plus 11 is that. Square root of that is 3.6 repeating. So I'm just trying to get a rough estimate of this. Does this work? And 5 times 11 over 9 plus 1, take the square root, is 2.6 repeating, which that actually equals positive 1 because it's the same amount of digits, but it's 3 minus 2. So that one actually does not work. So this solution does not give you the right one. So you just have to check. That's the problem. You can't just stare at the answer and say, oh, that works. So this one only had a single solution. And that is the end of the 2.5 problems that were similar to the ones that we did in class. Now, by the way, do not freak out. That double radical one is not on test 1. So do not worry about that in terms of what we're going to test you on. It's really just to show you the complexity level that these can reach. The one we did in class is what I told you was more like the level that you should be focused on. So you have the absolute value and the radical are the two most important things out of this section so far. What we do on our next class session, remember we have a quiz review and we have to finish this last piece, and I like to do it in class because it's just something that it's easier to talk about face to face. That last piece and the radical and the absolute value, those are the three big ones from 2.5 that are going to be test-worthy material. All right, have a good evening.